Building design involves many roles: architects, engineers, project managers, and so on. Currently, they use a file-based approach to exchange their designs. A typical project starts with the architectural design. The architect exports the model from software into IFC files and sends to engineers. Engineers reference this model for creating their own work in parallel. Afterwards, all models are fed into another software for clash detection. Users need to manually resolve the clashes before the next stage. The file-based approach has many problems. It is a sequential design. Users need to manually identify and resolve clashes. They also need to manage file versions on their own. We are imagining a future that embraces BIM cloud collaboration. You simply send the link, and everyone can edit the project from different devices simultaneously. But in BIM, the problem is more complicated. BIM incorporates many professional tools across disciplines and platforms. All of them use their own models instead of a single, holistic one. As such, the BIM collaboration platform must find a way to host the multidisciplinary data on the cloud and properly link the heterogeneous data at the object level. What will happen if they change their models? The system could monitor the change from one software and notify relevant users if their work is affected, like to provide geometry reference, or even offer intelligent suggestions to automatically resolve inconsistencies. Here we propose CBIM. User design in local software and use the CBIM connector to send the model to the cloud server, where it is represented as a graph. Same process for other discipline tools. Next, semantic enrichment algorithms generate inter-domain object relationships to link multidisciplinary graphs together. Those relationships could be design intent constraints, like the radiator could be attached to the wall, and the structural wall could be wrapped by the architectural wall with a corresponding relationship. After that, the mechanism monitors the change from any tool and computes suggestions to maintain consistency across models. CBIM compiles models as graphs and link objects together to enable intelligent applications. Let me show you our prototype. Here is an example. This project has an architecture model and a structure one. They are placed in two independent BIM software, both connected to the CBIM server. Now the architect moves the west wall to enlarge the room. Next, the architect uploads the change to the CBIM server through the CBIM Revit connector. In the cloud, the CBIM server receives the modification from the architecture software. This triggers the consistent maintenance mechanism to evaluate constraint relationships. The server detects violated constraints and attempts to compute propagation commands to resolve them. Consequently, within the structure software, the CBIM connector pops out the window, asking engineers permission to modify the model. If permission is granted, CBIM adjusts the beam and the columns automatically. If the change cannot be propagated automatically, as in the case of the bottom slab in this example, CBIM provides a geometry reference to support the design. Later on, the engineer pushes the updated design to the CBIM server. The server, in return, evaluates all constraint relationships once again and finds everything is consistent. A round of maintenance is completed. CBIM provides an object-based approach to enable BIM intelligent applications, such as automatic consistency maintenance we demonstrated in this video. This new way can enhance our cross-domain collaboration and improve working efficiency.